Assalamualaikum and good day. In this video, I'm gonna explain to you the question that arises. Why maximum damping ratio is 1 on the root locus plot in MATLAB? It is different what we have learned so far in the theory and the root locus. For example, here you can see that the damping ratio depends on the location of poles on the S-plane. For example, if this we focus on our root locus or the poles on the real axis. If the location of poles is multiple and in a location, then we have zeta equals to 1. However, when we have two poles on different location on the S-plane, it means that the zeta is greater than 1, right? However, when you plot it on the root locus, you will find that all zeta on the real axis equals to 1. So to answer this question, let's look at this prototype of the second order system. So we have here we have this open loop, or a diagram here is a unity feedback for this prototype second order system. So we have omega n square over s plus 2 zeta omega n. And when we find the closed loop transfer function, what we have is this prototype closed loop for the second order system, omega n square over s square plus 2 zeta omega n s plus omega n square. Let's demonstrate using MATLAB. So we have here, let's say we have omega n equals to 5. So I just take this arbitrary value, and I want to take zeta equals to 2. So let's do the transfer function using the this. I use s equals to tf s, and then I define by the diagram here. So I define omega n and s plus 2 zeta omega n. So it should have zeta equals to 2 and omega n equals to 5. And when we find the closed loop transfer function, we have this kind of transfer function. So let's run this first. And then you can see from here, when we plot the root locus, we need to use this diagram. Okay, we need to use the loop transfer function, which is omega n square over s plus 2 zeta omega n s omega n multiplied by h. So in this case, h is a unity feedback. So we have this term only. So we plot the root locus using this term. So I plot the root locus of the loop transfer function here. And what we get is we have this, right? And when we plot the step response of the system, so we need to use the closed loop transfer function. So I plot this, and you can see here it is clearly there is no oscillation. All right, so it means it is either zeta equals to 1 or zeta greater than 1. So we have defined earlier in this example that I use zeta is equals to 2. So this is actually an overdamped response. So the question is, when we put it on the root locus, you can see here the damping ratio will always be 1, regardless of the location of poles. Either it is we have two poles at different location, or if we have a single two poles at the same location. So to answer this question is actually you need to look at the algorithm, how to plot the damping ratio. So MATLAB define zeta equals to cos the angle of a point on the root locus here. So we can see here it is a function of cos. So when a function of cos, what we can have is actually we need we can calculate. So the cos is something like this, right? So when the theta equals to 0, so cos is equals to 1. So you can calculate by yourself cos theta. So where the cos 0, which is actually equals to 1. So that is why when we have the transfer function or the root locus here on the real axis, the value of damping ratio will always be 1 because it takes the cos theta. Cos theta. So that is why you will have always this damping ratio equals to 1. And we cannot get the zeta greater than 1 for the root locus. So actually you can find the root locus, the damping ratio is actually, you can show it using either calculation, or you can see from this step response here. You can also call for the step info, and for this step info we have all the information here, and we have the overshoot here. So the overshoot is 0, right? So remember the zeta and overshoot, you have the formula for that, and you can find the value of zeta from there, right? So I hope you understand why the MATLAB always show damping ratio equals to 1 for all the locations of poles on the real axis. All right, thank you for your attention, and have a try on your MATLAB at home. Okay, see you in the next video.